this is B. Naresh, working as a assistant professor in IEC department. The today's topic is analysis of CD JFET amplifier, where CD means common drain amplifier. So before going to this, we are going to discuss. We are going to utilize the FET is acts as a amplifier. Generally, we know that the FET is nothing but the field effect transistor. Why it is called as the field effect transistor means in that transistor, the drain current or the current controlled by an applied electric field between the two terminals. That is, one is between gate and source. Another one is drain and source. So that is the reason. And from that, so already we observed the characteristics of the FET. So we have two types of the characteristics. One is drain characteristics. Another one is transfer characteristics. From this drain and transfer characteristics, we observe that the drain current is a functioning of the two biasing voltages, that is VGS and VDS, where the VGS indication is gate to source voltage and the VDS indication is drain to source voltage. And we observed that how this drain current is controlled by an applied the biasing voltages between the gate and the source as well as the drain and the source ends. This type of the transistor is called as the field effect transistor. And again, generally, we know that the FET contains two types of the FETs. One is JFET, another one is MOSFET, where JFET indication is junction field effect transistor and the MOSFET indication is metal oxide semiconductor field effect transistor. And whatever the transistor, and the major application of this transistor is acts as a amplifier. So generally we know that when we consider the bipolar junction transistor, the BJT is also acts as a switch as well as the amplifier. So when the transistor is configured in a active region, we know that the transistor is acts as a amplifier. For this case, we observe that a small signal model of the transistor, either the BJT or a FET. So if you recall this, the small signal model of the FET or a JFET, and in that we observe that the drain current from that model, the small signal model, we derive that the drain current is represented as Gm times of VGS plus 1 by RT times of VDS, where we know this Gm is nothing but a transconductance and small rd is nothing but internal drain resistance, or it is also called as AC resistance. And this VGS and the VDS are acts as the two biasing voltage sources. One is the biasing voltage source between the gate and the source. Another one is the biasing voltage between the drain and the source. And from this, we drawn that JFET is simply replaced by, if you recall the JFET, either I consider this N-channel JFET. And generally, the FET contains the three types of the terminals. One is gate, another one is a drain, another one is a source. And most of the cases, if you consider the bipolar junction transistor, so if you want to utilize the amplifier, the best suitable configuration is common emitter configuration. And coming to this JFET also, or this FET amplifier also, the best common configuration is common source. From this, by using this relation, Poisson-Theorem equation, and from the small signal model equivalent, this transistor should be replaced with a small signal model. So let us consider the input side. If we consider the gate, this is the gate, and this terminal is the common terminal, is the source. And output side, we consider the drain terminal. Let us take this is the drain. Now I'm going to represent this parameter ID by using this mathematical relation. And the mathematical relation is for this JFET ID according to the small signal model. It is represented as GM times of VGS. Means this is the one current source, and this is again another current source, that is VDS by RD. Now we are going to represent the two current sources. Hence, the one current source is represented with GM times of VGS, and another current source is across the internal resistance. Means from this output side, if you want to write down this V naught is equal to I into R, means ID into RD. And in between these two terminals, we have the a potential difference between drain and a source, that is represented as VDS. Similarly, the input side, the potential difference between this is the gate terminal and the source terminal. Hence, the potential difference is represented as VGS. And this is the a small signal, means we apply the input voltage between the gate and the source. Output is measured across the drain and with respect to the source. And this is a small signal model or equivalent circuit for a JFET. So now we are going to analyze by using this small signal model and how we can define this CD, means the common drain is actually the perfect amplifier. Means what are the requirements to define the common drain is actually as a amplifier. And based on the terminals of the FET, so we have the three terminals. One is gate, another one is the source, and the third terminal is drain. Based on these terminals, we have the different configurations, the three different configurations. So we know that generally one is common gate configuration, and the second one is, we know that is common source configuration. Third one is the common drain configuration. So all these configurations we can utilize as a amplifiers, but we need to identify what type, means what amount of voltage gains and what type amount of input impedances and output impedance we need to offer to design a perfect amplifier by using this small signal model. So hence, in today's session we are going to discuss the analysis of common drain JFET amplifier using the small signal model. And before going to this, what is meaning of common drain? Means the drain terminal is common for input side as well as the output side. Means let us consider, if we maintain the drain is a common for input side and output side, the remaining two terminals we need to find out which terminal is acts as the input terminal and which terminal is acts as the output side. Hence, let us consider, we are going to consider the gate is acts as the input side and the source is acts as the output, and the drain terminal is for common for to represent this input terminal as well as the output terminal. So hence, by using this principle, now we are going to construct a common drain JFET amplifier. Then we are going to remodel into a small signal model. So from that small signal model, we need to identify the parameters like the voltage gain and the input impedance and output impedance to define how this common drain amplifier is acts as a perfect amplifier. So that is the reason. So what we discussed. So to define that one, so we discussed this one. The idea is a functioning of the gate to source voltage as well as the drain to source voltage. So by using this one, we derive a small signal model. From that small signal model, we represented this ID is equal to GMVGS plus 1 by RD into VDS. And again, we know one more relation, that is a amplification factor in a FET, that is defined as mu is equal to Gm into RD, where Gm is transconductance. Gm is nothing but transconductance. Again, the small RD means internal drain resistance, or it is also called as AC resistance. And in generally, we know that to define this one, this internal drain resistance should be much larger than of external load resistance. We need to define like that. So why? Because of that. So if you are maintaining the external load resistor is very large compared with the internal resistance, whatever the current is a flows or generates in effect, that should be flows through the internal resistance, not to the external load resistance. That is the reason to allow the maximum current at the output side, that output resistance or a load resistance should be very small compared with the internal AC resistance. Then only the maximum allowed current to be flowing through the load device or output device. Now we are going to design the analysis of so we are going to design this common drain JFET amplifier. So based on that, just now we identified that the gate terminal is acts as input side, source is acts as output, and the drain is common for input as well as the output side. So hence you remember this one. Let us take this is the JFET, and let us assume this is the gate terminal, drain, and source. Now we need to identify. So to allow the some amount of current, we require the some biasing, external biasing, or we need to apply a electric field between the two terminals. One is drain to source, and another one is gate to source. Let us consider if it is the N-channel JFET, and we know that the source and drain is made up with N-type material. Here I consider that the type of the JFET is N-channel JFET. And from this construction, we know that the source and the drain is made up with N-type material. And again, we know that in a FET, the conduction is depends upon only the majority charge carriers, N's. And when we consider the source and the drain is the N-type material, the majority charge carriers in a source is electrons. So why? Because of that, the source is always to give the charge carriers to allow the conduction in a FET. To repel the charge carriers or to diffuse the charge carriers from the source to the drain through the channel, we need to apply some amount of the electric field between the drain and the source. And based on the principle of the electron, so we know that this electron is a negative charge particle. Electrons are the negative charge particle. If you want to diffuse this charge particle or to repel the charge particle, we need to apply a negative field to the source. So hence, the source is biased with the negative pole of the battery with respect to the drain. So hence, the drain is biased with the positive pole of the battery, and the source is biased with the negative pole of the battery. Due to this applied electric field between the drain and the source, with the amount of applied force across this source, due to the amount of this force, the movement of the charge carriers are diffusing from the source to drain by passing the channel. Hence, the current flows from the drain to source. That current here it is represented as ID. That is the reason. So here, if you observe this principle, the drain is biased with the positive pole of the battery. Hence, it is represented as plus VDD with respect to the source. So source is connected to ground potential means that is nothing but a lower potential. And coming to your input side, so internally we require a biasing voltage. So here to limit, if you want to control the flow of this drain current or to limit this flow of drain current, again we need to apply a biasing voltage. Why? Because of that, from the N channel JFET, from the transfer characteristics, we drawn the transfer characteristics are drawn between drain current versus gate to source voltage. So what we observe from the transfer characteristics, when the VGS is a zero, when VGS is a zero, it offers a maximum current. That current is represented as drain to source saturation current. So when VGS is a zero means what happens when a VGS is zero means, so it does not apply any force between the channel ends. It allows the maximum drain current, and that maximum drain current is represented as drain to source saturation current. Whenever if you want to limit this flow of current, then the VGS should be reduced from the zero. Means, so in N channel JFET, that is a reason the gate is a biased with a negative voltage. Hence, the gate is biased with a negative voltage with respect to the source, and this reverse biased gate voltage to limit the flow of drain current. Hence, whenever the VGS is reduced from the zero, means towards a negative direction, we know that the drain current is also reduced. At very large reverse voltage, or at which voltage the drain current becomes zero, that point or that particular voltage is called as the pinch of voltage. So means at which voltage the drain current becomes zero at particular point, that voltage is called as the pinch of voltage, and this is also called as gate to VGS of voltage. The state is also represented as VGS of. So hence, at this point, we are representing as VP is equal to VGS of. Then, and along with these biasing voltages, to define an amplifier, a input signal is passing through the gate. So hence, now we are going to apply a input signal through the gate. But output is measured across the, so from this configuration, from this common drain configuration, we know that output is taken across the source. Hence, the load should be, means the external load or a load resistor should be connected across the source. That is the reason. At this point, from this source, so the load resistance is connected across the source and output is measured across this load. So hence we represented as the output voltage we are going to measure across the output load, and the load is connected through the source terminal. Hence this load resistance here it is represented as RS. So why? Because of that the load is connected across the source terminal, hence it is represented as a load resistor that is called like the source resistance. Now the drain is a common for to measure the input and the output with respect to the gate and the source terminal. And this is your source, a AC source. So means your applied input signal is passing through the gate terminal with a gate biasing resistance. That gate biasing resistance, so it is represented as RG. So generally from that characteristics, we observe that to allow the minimum gate current means, so our aim to be the maximum whatever the charge carriers are repelled from the source, the same amount of charge carriers to be reached to the drain, we need to maintain the gate current should be, or gate voltage should be zero. So means to maintain the gate current should be minimum, so we need to offer a very large input impedance that is represented as RG. So this is the construction for a common drain JFET amplifier. So hence So if you observe this circuit, the input is passing through the gate terminal and output is measured across the source, and across the source we connected the load. That load is represented as RS, or it is also called as source resistance. So to analyze this amplifier analysis, we need to convert the JFET into the small signal model. So hence I'm going to redraw into a small signal model for this circuit. So if you want to redraw this into the small signal model, we need to recall this function. So we know this ID is equal to Gm into VGS plus 1 by RD times of VDS. And generally, we know that the JFET, this is the JFET. Now I'm going to replace this JFET with a small signal model. So how we are going to replace here? This is the input side. This terminal is represented as a gate, and output side it is drain. So this is drain. And now we are going to represent a common terminal is source. Let us take this is the source. Now we know that so a drain current is a flows. What is the equation? By using this mathematical relation, ID is represented as Gm into VGS plus 1 by RD into VDS. Hence, it is represented as Gm into VGS plus another current source is passing through this internal drain resistance RD. So this is a model for a JFET. Now we need to use this analysis, input circuit analysis. So across the drain, it is internally biased with the VDD. Now we need to measure a output voltage across the source or across the load resistance, that is called the source resistance. Hence, I am going to redraw in terms of the circuit. So then from this source, so we have the load resistance. Hence, I am going to place a load resistance or a source resistance, that is RS. It should be connected to ground. Then your input is applied between the gate and the lower potential. Hence, now we need to apply a input source, that is Vi, between the gate and the lower potential. This is the lower potential. So up to this point, we know that this is VGS. And now we are going to represent output parameter also. If you observe this circuit, the output voltage is taken across the load resistance. So here, which one is the load resistance? RS is acts as a load resistance. Hence, now I'm going to connect. This is the my node, output node. V0 is taken across the output resistance or a load resistance, or it is also called as a source resistance, that is represented as RS. Now, if you observe from this circuit, so this is the equivalent of a small signal model equivalent circuit for this common drains JFET amplifier. Now, by using this map circuit, now we are going to analyze the important parameters like the voltage gain and the input impedance as well as the output impedance. So if you use this circuit representation, so just I'm going again rewriting the circuit. So this is gate and this is drain side. Gm into VGS and this is the RD. Source side RS. Now we are going to measure the V0. So which current is the flows ID. And now it should be connected to Vi. Up to this point, this is VGS. And so now in between this, again we connected one resistance, internal resistance. Sorry, the extra input side RG. So from this, we can take this is let us take this is some current flows IS. So means that if you want to write, if you, the input side, if you apply the KVL, so what is this? This VI is equal to the summation of from gate to source, that biasing voltage, the potential difference between the gate and the source voltage is represented as VGS, along with from that source to a lower potential. This is the lower potential. We have another resistance, that is a load resistance or external resistance or output resistance. And across this output resistance, we are going to measure a parameter, that is output voltage. So hence, can I rewrite this? For parallelly, the voltage is same. So hence, from this, the VI is equal to, if you apply the KVL at this input side, the input voltage VI is represented as the summation of this potential difference between gate and the source, along with the voltage drop across this source resistance or a load resistance, that is RS. Hence, from this circuit, I represented as this VI is equal to the summation of VGS plus V0. But we need to define, and we know that from the FET configuration, the drain current is a functioning of VGS as well as the VDS. So hence, from this relation, we need to find out how much a potential barrier is generates between the gate and the source, that is represented as, if you take in the VGS, then take this V0 is outside, hence the VGS is equal to VI minus V0. So you remember this one, the VGS is from the circuit, from the small signal model, the VGS is represented as the difference between the input voltage and output voltage. We can also write like this, VGS is equal to VI minus V0, means either ID into RS, or you can also write IS into RS. Clear? So now, and again, if you take this again circuit from the small signal model circuit and gate, this is VI. Let us take the drain, GM into VGS, and this is RD, and external load resistance is RS, and this is V0 node. This is connected to ground, source, drain, and here the current is ID. So up to this point, this is VGS. Now we connected as a external resisting gate side RG. Now from this circuit, now I'm going to find out the V0. So means generally, so across the source, we know that source current is a flows. So means let us take, if from this node, again from this node, and the current is leaving from through this internal AC resistance as well as the external load resistance. If you remove this drain from the voltage source, if it is connected, the equivalent, if suppose if you want to find out the equivalent resistance at the output side, and internally the drain is a biased with VDD. If you remove this VDD and it is connected to a ground potential, or means we can say it is a short circuit, then what happens? And we know this RD is parallel combination with means the internal drain resistance is a parallel combination with the external load resistance or a source resistance. So generally, we know that the current flowing across the source terminal is represented as V0 is equal to IS into this equivalent resistance, I represented as R equivalent. And again, from the FET construction, we know that the source current is equal to gate current as well as the drain, the summation of gate current as well as the drain current. And from the FET construction, the gate current is very, very small. Hence, I'm going to assume the gate current is 0. Hence, IS is approximately equal to the drain current. Hence, that is the reason. So, here I'm representing this V0 from this representation. V0 is equal to this IS is replaced with ID into R equivalent circuit. So, what is R equivalent? This R equivalent is nothing but the parallel combination of internal drain resistance and the external load resistance, that is RS. So hence, I represented as this V naught from this circuit, from the circuit. V naught is represented as ID times of RD is parallel with RS. Now let us consider again, and to allow the maximum current, whatever the current is generates across a field, we need to allow it to the load side. So to allow the this drain current across the load side, we need to assume that internal drain resistance must be much greater than of external load resistance means, and we know that at the output side, the equivalent resistance is represented as RD is a parallel combination with RS. Whenever the two resistances are unequal and they are in a parallel combination, the equivalent resistance is equal to the smaller resistance value. Hence, the maximum drain current through flowing through the smaller resistance. So based on that, I assume this ID is equal to, if I neglect this one, the current is the maximum current flowing through this smaller resistance through this low side. Hence, I assume this ID is equal to Gm into VGS. From this one, ID is equal to Gm into VGS plus 1 by RD into VDS. Hence, I consider this the maximum current flowing through this current source. Hence, ID is equal to Gm VGS. Then I'm going to substitute this one in a V naught term. So V naught is equal to Gm into VGS. And the equivalent resistance is RD is the internal drain resistance is parallel combination with external load resistance or source resistance, that is RS. So just now we observed from this input circuit, what we observed, Vi is equal to, from the input side, we observed that Vi is equal to the summation of VGS plus V0. From this, we derived that the VGS is equal to Vi minus V0. Why? Because of that, to define, now we are going to define the voltage gain. So if you are going to define the voltage gain, generally we know that the voltage gain in terms of output voltage and input voltage. Hence, the unknown parameter, all the unknown parameters, I am going to convert in terms of only the input voltage and as well as the output voltage terms. Hence, so from this circuit, we observe that the VGS is the difference between the input voltage and output voltage. Hence, I am going to substitute here the VGS is equal to the difference between VA and V0. So hence I substituted this one. Gm times of VGS is replaced with VA minus V0 is a product with a parallel combination with R equivalent. You can take R equivalent. That R equivalent is nothing but RD is a parallel with RS. So hence just can expand the term, multiply with this term. So what happens here? So if you multiply this term, so from this V0 is equal to Gm into VA into the parallel combination is RD is a parallel with RS, and similarly minus Gm into this term is a V0. Again the R equivalent is RD is a parallel combination with RS. Hence we got this relation. So V0 is equal to this relation. So from this, again the two V0 terms is there. You can take it outside. Now what happens, this one, so that becomes, so when you take in the outside, so means it becomes V0 plus Gm times of V0 into RD is a parallel with RS, that is equal to Gm into Vi, RD is a parallel with RS. Hence I represented. So from this, what we observed, so here if you take the V0 is a common term, so means V0 is the common term, 1 plus Gm times of RD is a parallel combination with RS, that is equal to Gm Vi into RD is a parallel combination with RS. Hence the same expression I represented when we simplify this relation. So V0 of 1 plus Gm is a parallel combination with RD and RS, that is equal to Gm Vi in the parallel combination with RD is a parallel with RS. So from this, we are going to define the output voltage. So what is the output voltage? So just take the only V0 term. So hence V0 is equal to, we take this term is outside, means it becomes division. Gm into Vi, the parallel combination of RD and RS by 1 plus Gm times of RD is a parallel combination with RS. So this is the output voltage we derived from the small signal model of the JFET with respect to the common drain JFET amplifier. Now, by using this mathematical relation, now we are going to find out the voltage gain of the common drain amplifier. So, if we consider the voltage gain, so what is the voltage? Generally, the gain means it is defined as output parameter to the input parameter. So here we are going to define the output voltage gain. So the voltage gain is defined as it is a ratio of output voltage to the input voltage. And where we observe this V naught is equal to, what is the term we observe? V naught is equal to Gm into Vi times of Rd is a parallel combination with Rs divided by 1 plus, so Gm times of Rd is a parallel combination with Rs. Then it is divided with the input voltage, that is a Vi. Hence this Vi is a get cancel. Hence we observe this V naught is equal to Gm times of Rd is a parallel combination with Rs by 1 plus Gm times of Rd is a parallel combination with Rs. Now, and already we observed that, so to allow the whatever the current is generates through the in this fed, that should be allowing through the load resistor or a load side, we need to maintain from that common drain amplifier. If you are observing, you have the two resistances, say one is internal drain resistance, another one is a load resistance. So our aim to be, we need to offer whatever the current is generated, that should be flowing through, maximum current is flowing through the load side. Hence, we are going to assume one condition, the Rd should be much greater than of Rs. And under this condition, if let we consider this Rd is a much greater than of Rs, and we have this equivalent resistance. What is the equivalent resistance? This R equivalent is represented as Rd is a parallel combination with Rs, means Rd into Rs by Rd plus capital Rs. And we know that under the parallel combination, the two resistances are unequal and they are in a parallel combination, that equivalent parallel resistance is approximately equal to smaller resistance. Hence, under this assumption, this R equivalent is equal to the smaller resistance, that is load resistance is nothing but Rs. Hence, under this condition, I am going to simplify this relation. So the voltage gain AV is represented as V naught by Vi, that is equal to. So under this parallel combination, when if Rd is a much greater than of Rs, that is equal to Rs, and simply I will represent it as Gm times of Rs by 1 plus Gm times of, again, this is the parallel combination, and this R equivalent is approximately equal to the source resistance when Rd is a much greater than of Rs. Hence, this is Gm into Rs. So, when if you observe this parameter, generally it should be less than of 1. If you observe this relation, what is the voltage gain relation? AV is equal to, it is represented as Gm times of Rs by 1 plus Gm times of Rs. From this relation, it is always less than of 1. Or we can take the Gm Rs is much greater than 1, then we can declare this is Gm times of Rs by Gm times of Rs, then it is equal to 1. Means, so in a common drain amplifier, the voltage gain, when we are just observing this mathematical relation, the voltage gain is always less than 1, or it is very nearer to the 1, means or approximately equal to 1. So from that, we can say that it is also called as a source follower circuit, a common source follower circuit. And hence it can be used as a buffer, the common source follower circuit, or from this voltage gain representation. Why? Because it satisfies the unity gain follower circuit. So it is also called as unity gain follower circuit, or a common source follower circuit, or a common drain. These circuit means this circuit, common drain amplifier circuit, can be used as a buffer due to the effect of this voltage gain of the common drain amplifier. Then now we are going to observe the remaining two parameters like input impedance and output impedance. So if you observe the input impedance from the circuit, let us consider this is a circuit. From this small signal molar circuit, the input side, which type of impedance is offered? Only the input impedance is offered. Hence, directly here I represented as Zi is equal to RG from that equivalent circuit. So similarly, we are going to calculate the output impedance. So means if you observe the output side, we have this one. I'm going to draw the output side only. This is GM into VGS, and one more is small rd along with a source terminal contains a load resistance Rs, and here we are going to measure this V0, and this is the drain terminal, and here it current flows ID current. So here I considered only the output circuit, and if you use this output circuit, now we are going to find out the output impedance. We know that it is a ratio of voltage to the current, means we are going to measure at the output port, hence it is defined as output voltage to the output current, that is V0 by I0. So from this circuit, the current means which one is output current, the drain current is output current, hence I represented as I0 is replaced with the drain current. And just now we observed this V0. What is the V0 term we observed? V0 is equal to GM times of VI. RD is a parallel combination with the RS by 1 plus GM times of RD is a parallel combination with the RS. And when the input voltage source is when the input voltage is short circuit or input voltage is constant. Under this condition, and we observe that, and again from the circuit, ID means the maximum current flowing through this one. Hence, from this we represent that ID is equal to GM into VGS, and VGS is nothing but here we can take it as a VI, hence GM into VI. So hence I consider that ID is equal to GM into VI. Now you can substitute this one. So means if I'm substituting this one, Z0 is equal to V0 means this one GM into VI. RD is a parallel combination with RS by 1 plus GM times of RD is a parallel combination with RS by, and ID value we taken as GM into VA. Okay. So from this representation, so this GM VA is a get cancelled, hence the Z0 becomes RD is a parallel combination with RS by 1 plus GM times of RD is a parallel combination with RS. If we simplify this relation, so means what happens? RD is a parallel combination with RS means RD RS divided by RD plus RS by 1 plus GM times of RD RS by RD plus RS. If we simplify this relation, so if we take the LCM, now what happens? This is RD into capital RS by, just take the LCM means this is small rd plus capital RS plus GM into small rd into capital RS by, so this is actually by RD plus RS by, this is RD plus RS, means this RD plus RS is a get cancelled. Now that is becomes Z0 is equal to this one. So if we simplify this one, now Z0 becomes RD into RS by RD plus capital RS plus GM into RD into RS. So we can also write this is GM into RD is nothing but a, we know that amplification factor mu here. So hence from this relation, so I am going to write again. So from these two terms, if what happens, RS is a common, hence if I take in the RS is a common, now it becomes 1 plus GM times of RD. We show the one more relation, this is also valid, Z0 is valid. If you want to show in terms of some amplification factor for a common drain amplifier, now I'm going to take this is a common term both in denominator and the numerator. So I'm going to divide with this factor in both the denominator and numerator. Means what happens? RD into RS is divided with 1 plus, so means this factor I'm going to define 1 plus GM into RD by, so here this is RD by 1 plus GM into RD plus it becomes RS. So this I'm going to write. So this is RD by and GM into RD. We know that amplification factor is equal to the product of transconductance and internal AC drain resistance. Hence, I'm going to write this is 1 plus mu times of RS by this is again RD by 1 plus mu plus RS. So from this we can say that the Z0 is represented as RD by 1 plus mu is a parallel combination with the RS. The output impedance of the common drain amplifier is another one more relation is the output load resistance and this the parallel combination with the RD by 1 plus mu. So up to this point in this today's session, we observed that what is a common drain amplifier and we designed the common drain amplifier using the small signal model and also we observed that voltage gain, input impedance as well as the output impedance. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.